Today I will present to you some parts of the studies that I have done during my PhD. My research focus is on reconfigurable intelligent surfaces. I will investigate that topic from the channel modeling perspective, system design perspective, and I will show you our practical measurement results during that presentation. So first I will give the motivations and fundamentals about the RAS, and then I will briefly summarize our channel modeling steps, methodologies, and then I will present our coverage extension solutions for RAS-empowered communication systems, especially for millimeter wave frequencies. And then I will share our practical measurements for indoor coverage enhancement. Then I will conclude with my final remarks. Okay. As you know, the wireless community has witnessed a very exciting period in which the standardization of 5G networks and now academia and industry have set their sights on 6G wireless technologies and beyond by starting active research campaigns. And researchers have already started research on 6G technologies by escaping from the comfort zone of 5G-oriented solutions. And 6G wireless systems are expected to provide broadband connectivity by supporting new use cases, including extreme capacity and very high mobility. Actually, 6G in the 6G wireless systems, we expect to provide broadband connectivity by supporting that use cases, but we need some attractive use cases might only be possible with effective physical layer technologies such as ultra-massive MIMO, millimeter wave and teraband communication systems, and also reconfigurable intelligent surfaces, which is the brand new technology that recently get pretty attention from the industry and research community. And in the wireless communication environment, the propagation medium is a randomly behaving entity between the transmitter and the receiver. And it's degrading the quality of the received signal because there are uncontrollable interactions of the transmitted radio waves with the surrounding objects in the environment. And we know that the received signal power decays with path loss, shadowing, and multiband fading effects. And also, when an electromagnetic wave hits the surface, it will be reflected, scattered, or refracted from that surface. But that reflection characteristics depends on the inherent properties of the materials and that surfaces. So here, can we exploit that randomness of the channel, the place in the environment? So can we manipulate that kind of reflections, scatterings, refraction of incoming waves? This is where RAS comes into play. By using RAS, we can adaptively control the characteristics of the wireless channels, and we can adopt some properties by considering the characteristics of the channels. That RASs are man-made surfaces of electromagnetic material, and they can be electronically controlled with integrated electronics. And they have a unique and adaptive wireless communication capabilities. As we know, in 5G, we have software-controlled networks. So here is the question: can we extend this idea to software-defined and smart radio environment in the 6G wireless networks? This is the motivation of RAS. And RASs you can see different terms: reconfigurable intelligent surfaces, intelligent reflecting surfaces, intelligent surfaces, walls, reflect arrays, metal surfaces, whatever. All of the concepts are very similar. We can just mention during the presentation as reconfigurable intelligent surfaces, or RAS, and that RASs are smart devices that control the propagation environment with the aiming of improving the coverage and signal quality. As you see from that video, if you have blockage of, if you don't have high signal quality, you can put RAS on the environment, and you can create additional alternative transmission path when you don't have reliable direct link between transmitter and the receiver. When you look at the material structure of that surfaces or implementation of that surfaces, the most common implementation is reflect array types surfaces. And in that surfaces, we have 3 layers. On the top, there's the electric substrate. On the mid layer, there is a copper backplane. And at the bottom, there's a control network. And we have controller. We can manipulate the properties of each reflect array with that RAS controller dynamically. If we look at that video, here we see that just one small reflecting element on that surface, and that elements consist of PIN diodes or varactors, and by changing on-off states of each diodes, you can create different radiation or reflection characteristics. Here, if that array element has 2 diodes, you will have 4 possibilities: on, off, on, or off. So each variation means that you will have different reflection characteristics. So, and if you have multiple reflect arrays, you will have a lot of possibilities for reflection. And you can adjust this by considering the current realization of the channel. This is a very good degree of freedom for us when we design system. So first, I want to mention about our channel modeling efforts in RAS-empowered wireless communication systems, and I will share our cluster-based statistical channel model methodologies, and I will introduce our open source seamless channel simulator by following that channel methodologies, and then I will share our results by using that open source simulator. And RAS-empowered communication has received growing interest from the wireless research community due to its undeniable potential in extending coverage, enhancing the link capacity, mitigating the interference, fading and Doppler effects, and increasing the physical layer security. These are the most common use cases in the literature. Against this background, there is still an urgent need for a physical and widely applicable millimeter wave channel model to be used in various RAS systems in indoor and outdoor environments. Millimeter wave is important for RAS because if you have strong direct link and in the sub-6 GHz, and the possibility to have that kind of strong link is higher than the millimeter waves. And millimeter wave frequency is susceptible to blockage. So the best beneficial use case is, in my opinion, is millimeter wave. So we focus on higher frequencies during our channel modeling efforts. In our work, in our studies, we aim to fill an important gap in the open literature by providing an accurate, open source and widely applicable RAS channel model for millimeter wave frequencies. And in our book chapter, you can see from here, and we summarize all channel modeling efforts in the RAS literature. And generally, there are 2 different approaches. First one for path loss modeling, and you can see 2 different categories in that topic. First one is near field path loss modeling. Second one is far field path loss modeling. You should properly evaluate that path loss characteristics by considering the positions of the terminals. Because if you are in the near field, and it is more reasonable to consider near field cases for RAS, because when you put RAS, receiver can approach that area, that coverage area of the RAS during the transmission. So you should consider also near field cases. And another topics for channel modeling is end-to-end channel modeling, and this is more important than path loss modeling, because you should also include path loss modeling here. There are three different approaches here. First one is physics-based modeling, which is related to free space optical literature, and second one is statistical modeling that we used in our channel modeling studies, and third one is mutual coupling based modeling. There are recent works in that topic also, and these also are important for continuous surfaces, actually, mostly. Here is the list of the channel modeling studies in the literature, and you can see the contributions of that studies. In the last row, you can see our studies in that area, and especially in millimeter wave frequencies, using an RAS in the transmission can enable additional transmission paths, as I mentioned earlier, when the direct link between the transmitter and receiver is blocked or sufficiently not robust. Modeling a physical, open source, and widely applicable millimeter wave channel model for RAS systems is a great importance to shed light on realistic use cases of RASs in future wireless networks. Because there are a lot of steps when you deploy the RAS. You should design RAS, you should design the system properly, and you should be sure the physical characteristics of the RAS before you design. So you can just use the well-known distributions when you model channel. This won't show the real effects of the channel. So this is why we started to search that topic 3 or 4 years ago. And in our studies, a unified narrowband channel model for RAS systems is introduced by including the 5G millimeter wave channel model in the standard documents with a random number of clusters, scatterers, and the characteristics of the RAS. We consider all of that kind of parameters. Here is the generic system model of our channel modeling studies. We have first SISO case here. As you see, we have transmitter, it's in the fixed position. We have RAS, it's again in the fixed position. And we have clusters, scatterers. And in that work, unified narrowband channel model for RAS for both indoor and outdoors are introduced for the first time. We consider the 5G 3D channel model with random number of clusters, scatterers, and we include many physical characteristics such as line of sight probability, shadowing effects, shared clusters, realistic gains, and array responses. This is the channel modeling steps for indoor and outdoor environments. The first 6 steps are similar, but after that steps, you should follow the different paths by considering your indoor and outdoor cases. In our simulator, we follow that steps. We determine first positions. When you know the positions of the terminals, you can also produce the clusters, the scatterers by following the proper distributions. Then you can calculate the angles, you can produce the array responses. And finally, you will obtain 3 sub-channels. Let me show that figure again. Here, you have transmitter RAS channel, RAS receiver channel, and transmitter receiver channel. We need to obtain these 3 channels separately. And this is the steps, producing steps of that. And after that, you can write that system model. And when you know the channels and when you produce the channels, you are free to adjust phase adjustment by considering any methods. It depends on you. We are producing G, H, and H ISO and give you that channels with our simulator. I will show you the interface also. And you may use that in your research. This is the channel.
Do you mind if I interrupt for a second?
Of course, Hocam.
Yeah, in this slide, you said that we have to estimate all 3 channels separately. Why? I mean, what happens if we just estimate the composite channels through the IRS?
Hocam, because you may not have direct link most of the environment, and you should want, when you design the system, if you have a strong line of sight link, and if you're sure that, for example, if you want to design a system, you have RAS in the environment, you should maybe deactivate that RAS if you have strong line of sight.
Actually, if you go back to your previous slide, I was just trying to say this one. Just one channel through the IRS. Let's estimate this separately, and we'll estimate the direct link separately. But I mean, the first channel is from the transmitter to IRS, and then it's concatenated, not concatenated, but kind of a multiplication. It is multiplied with that IRS to the receiver channel anyway. Do I really need them separately? That's what I'm asking. Not the line of sight versus the path through the IRS, but the path which passes through the IRS.
Actually, the clusters or objects in the environment is important. When you understand that structure, and you may obtain that channel separately. Actually, this is not mandatory when you make physical implementations. I will show in my last slide that you don't actually, when you design system, you may reduce that dependency of obtaining all channels separately or independently. But when you want to use RAS, we should first, when we first try to understand RAS, we wanted to understand the relations between that channels. We've also investigated, correlations of that separate channel to understand that systems properly. And your phase adjustment method is important here. You may try to optimize that RAS-assisted link. And in some cases, that will be enough. Because that will reduce your complexity when you adjust the RAS phases. You may think that if you have MIMO, if you have multiple RAS elements, and if you have multiple PIN diodes, that will increase the computational time. So, if you know that kind of details, you may just design, systems. You don't need to make brute force computations like that. Actually, this is for understanding of the RAS-assisted systems. And then, we have line of sight. Your RAS-assisted link can contribute that line of sight link. You can maybe try to align phases of these 2 links separately. And there are different kind of approaches here. You may just try to improve end-to-end channel end-to-end channel gain. This is one way. Another way, you may just improve if you don't have strong direct link. You may just try to improve the array-assisted link, that link with array phases. And this is related to that matrices, array phase shift matrices, actually. How do you adjust that? In that question, you may choose different topics. We just wanted to give framework about that.
Okay, thank you.
And actually, in our physical measurements, we just consider end-to-end channels. Normally, in physical environment, you cannot obtain that separate channels. But if you know the environment properly, you may estimate, you can say that I have that kind of link here, and I may try to just improve that link.
Mm-hmm.
Can I add a question here, if you don't mind?
Of course.
Can you go back to page number 10, please? So
yes.
In this y is equal to expression, do you estimate G and H channels separately?
G and H, yes. We are modeling,
I see. So
separately.
how do you do that? I mean, do you put some active elements on the array system?
This is not channel estimation, actually. We are, producing channels. Normally, when you have some, realization in the environment, normally you cannot estimate with passive elements. Transmitter array sync, you need active elements and semi-passive channel estimation methods. This means this is actually a topic for channel estimation for array structure. But you may check that semi-passive channel estimation. How it works, you have some active elements on the arrays. Not all of them active, but for example, if you have 200 elements, just 10 of them can be active. During channel estimation, you can activate that elements. You can estimate channels. Then during the transmission, you can use the passive elements to adjust phases.
Okay, thank you.
Okay.
Thank you for the answer.
Yeah, okay, you're welcome. And there are different kinds of channel estimation techniques for also arrays, but that will increase the channel estimation burden. Normally, when we design system, we try to get rid of that burden, actually. Okay, this is the array geometries of our arrays in our channel modeling. And we are calculating the array response vectors by considering that geometry. We are using Cosq radiation pattern for arrays elements. And we have attenuation parameters, normalization parameters here, and arrival and departure angles to calculate that channels. And in our methodology, our number of clusters parameters follow Poisson distribution with variance lambda p. Lambda p depends on your operating frequency. When you change the operating frequency, you should use the appropriate lambda value from the standard documents. And for subarrays, I mean scatterers within the clusters, we are using uniform distribution. For azimuth elevation departure angles, we are using conditionally Laplacian distributions with theta and phi means, and that means follow uniform distributions. And after our extensive simulations and variations, we defined that and modified that parameters by considering the arrays use cases. The fundamental difficulty in modeling of a wireless channel involving an arrays arises from, once C clusters as well as their subarrays are randomly generated, And the azimuth and elevation arrival angles for an RS cannot be modeled random as in 3G BPLT and 5G spatial channel models due to the random orientation of mobile receivers. You should also consider the fixed position of the RS when you model that sub channels, and you should modify some parameters when you design systems. This actually system model for indoors. Actually, we also provide channel model for outdoors in our work. I will just briefly show from that indoor channel modeling, but we can easily extend that model. And we consider the channel parameters reported in that work for indoor hotspot office environment and urban microstreet canyon for outdoor environments. And these are summarized in this table, that parameters. We are considering for both non-line of sight and line of sight cases, depends on your system model. And we also consider the line of sight probability. This is very important for RAS because if the height of the RAS is not smaller than that of the transmitter, we assume a clear line of sight path between them. If you put transmitter here, if you put RAS higher distances, we assume that we have clear line of sight. The positioning is important. So we are considering that kind of spatial use cases in the channel modeling. Depends on your input parameters. I will show you that. G is the channel of RAS and receiver. And we have transmitter RAS direct channel. We are calculating that parameters, as you see from here, by calculating also that angles by considering the parameters that I mentioned earlier. And this is, we can easily extend that indoor channel modeling strategy to our outdoor environments by modifying certain system parameters. Differences in the positions of the RAS and terminals in an outdoor environment will cause changes in channel parameters while following the same channel modeling strategy, particularly path loss exponent and shadow fading parameter sigma can be adjusted according to the given outdoor propagation environment. In terms of small scale fading, only for the clusters whose angle of departure points toward the ground, we may reduce the maximum distance by considering the terminal distances in outdoor environment. The major change in contrast to our indoor channel model will be in the channel between RAS to receiver, which might be subject to small scale fading as well in outdoor environments with random number of unique clusters, because the distances will be higher than in the indoor case. So the dependency between the subchannels or correlation will be less than the indoor cases. So these will be these efforts actually will be guidelines towards the effective use of RASs for both indoor and outdoor cases. So by following that methodologies, we also provide open source, accurate and widely applicable RAS channel model for millimeter wave frequencies. This is the graphical user interface of our seamless channel simulator. This is the version 1. And we have user selectable parameters here. For example, environment, you can choose indoor and outdoor environment. You can change the position of the RAS. You can change frequency. We have here 2 frequencies, 28 GHz and 73 GHz. And you can enter number of RAS elements really, and you can also determine the number of channel realizations for Monte Carlo simulations. And then you can also enter the transmitter, receiver, and RAS locations. And when you click the Run Simris button, you will obtain 3 different sub-channels. And you can use that channels on your simulations. You can easily create in your MATLAB, you can easily use that methods continuously in your simulations. You can access that course from our Core Lab websites. I will share also that simulations. You can also check. This is the simulation results obtained by using our Sims channel simulator. If we check that first figure for indoor office space, when we look at that green and purple curves, the purple is for 64 reflecting elements, and green is for 256 reflecting elements for RAS. When we improve the number of reflecting elements, we see that we obtain noticeable increase in axial rate performance. This is not surprise, but the key point here is that Z is the vertical distances of RAS in the environment. So if we check that yellow and green line, the reflecting element numbers are same, but the height of the RAS is different. So when you increase the number of height of the RAS positions in the vertical line, as you see that you will obtain significant improvement in the axial rate performance, because you will increase line of sight probability. When you increase line of sight probability, the loss component of that sub-channels will be strong. So, for that kind of use cases, when you understand that basics of the RAS, you can properly design efficient systems by considering that probabilities also.
Ibrahim, have you described the shape of the IRS, the reflecting intelligent surface you're talking about, or is this distance 2 meters? Is it the lower edge of the reflecting intelligent surface, or is it the height of the wrist itself?
Actually, not height. The vertical distance from the ground of the middle point.
Oh, the middle point.
Middle point. Yeah, from ground, from the middle point of the RAS. This is the in the 3D Cartesian coordinate systems. This is the z-axis, the vertical axis. This is the coordinates of that axis. We are considering the center point of the RAS.
Okay, and how about the dimensions? So yeah, the midpoint is at 2 meters, but how large is the IRS? And how, maybe you will show that kind of results, but how does your channel model change if, for example, what happens if I use a rectangular wrist, which is wider in the horizontal dimension, or what happens if it is a square, or how its dimensions, how does it affect the final result here?
Dimensions will mostly affect, near field fields. Actually, when we increase dimensions, we limited the number of elements with the case of near field boundary. When you increase a lot, you will be in the near field, and you should start from advanced when you model the channel. So, we, recommend to increase limitedly, but when you use millimeter wave frequencies, you can easily use 1,000 elements, 2,000 elements. You may see some demos of RASs for millimeter wave. It won't exceed to 50 centimeters like that. Actually, it's not huge. Actually, it's very small because you are in the millimeter wave frequencies. Each reflector rate will be very small, tiny elements. It's not big issue actually for that, because if you want to use, for example, 10,000, nowadays it is not so possible, because you should consider the computational complexity also. But the dimensions nowadays are reasonable, even if you use 2,000 elements. It's not huge for millimeter wave. And I will show that we have one prototype for sub 6 GHz or 5 gigahertz. And we have just 76 elements. But we have also millimeter wave arrays for 28 gigahertz. It has more or less 1,000 elements, but it's very smaller than sub-6 gigahertz arrays.
Thank you.
Okay, you're welcome. Here we investigate the effect of varying receiver positions through the X and Y axis in the environment, and we obtain actual rate performances for that. We have that transmitter and arrays positions, and we are changing the locations of the receiver. And here the highest achievable rate is obtained when the receiver and transmitter is close to the each other. Because if you have strong line of sight, you don't need arrays. But when the distance between transmitter and receiver is higher, you should include arrays. And here, the most sensitive parameter here will be the separation between arrays and receiver. So if you don't have strong line of sight, you may put arrays to near positions of the receiver. So our channel modeling effort has been a first step towards physical channel modeling for emerging arrays and power networks. This is not exact channel modeling, actually. This is the first step, because if you want to do channel modeling, you should make extensive practical measurements, thousands of measurements to fit some distribution. And our channel simulator can be used effectively in channel modeling of array-based systems with optional operating frequency, terminal locations, number of arrays elements, and environments. The fundamental aim of this study is to pave the way for an accurate channel model which is compatible with real-world experiments. And it's open source, so you can download and you can change the radiation pattern of the arrays easily by using this source code. And you may include some different properties. And some students sent me an email and they said that we include polarizations to your system models, like that actually. And in our different magazine paper, we provide emerging applications and use cases of array-assisted communication systems in future wireless networks. And there might be different use cases for cellular connectivity, physical layer security, NOMA systems, and you can use arrays for localization or improve the accuracy of the localization. You can use also in indoor couch extension, in vehicular networks, Doppler mitigation, non-terrestrial networks, UAV-based systems. You can see different kind of topics in the literature. In this work, we take a step back and approach arrays-empowered communication systems from the perspective of the physical channel modeling to shed light into their practical use cases in future wireless networks. We also proposed Siemens Channel Simulator version 2 by including MIMO aided transmit and receive terminals into its earlier versions. We have MIMO extension here, and in the graphical user interface, as you see, you can change the array types of transmitter and receiver as planar and linear array types. You can have rectangular array or linear array. You can change that type. You can adjust the locations again, and you can adjust the number of transmitter and receiver antennas here. We extend that idea and consider the possible use cases for future wireless networks. This is our channel matrices in our MIMO cases. You can produce that GH and DE channel matrices from our simulator. And here, by using that MIMO version, we obtain some results. For example, if you have two arrays, this is the top view of the considered transmission scenarios. We have two arrays in the environment for different poles. So we assume that we have 7 test points. For each point, we measure the achievable rate. First, if we don't have any arrays, and if we just activate RAS1, and if we activate 2 of the arrays in the environment. For each test points, we have 3 different achievable rate values. This second terms in that form. So, in the case of only RAS1 being operated, an average increase of 26% is achieved in the achievable rate of the reference points. Averagely, we can improve the system performance for all points. But while an increase of 45% is achieved when RAS1 and RAS2 are jointly activated. Because more or less, roughly, I plot that coverage areas with red and green, yellow color here. And if you are close to that RAS1 region, RAS1 will be very, efficient in the system performance. But if you are in that regions, activating 2 RASs will be more beneficial. But if you are in the 0.4, you will also obtain higher achievable rate performance, even if you don't have RASs in the environment because of the dielectric. But again, if you have also strong dielectric, you can again improve the system performance by activating these 2 RASs. Yeah, we have link, but we can improve the performance of that link also. Another point here is that using a large number of antennas in the MIMO systems or massive MIMO systems enhance the achievable rate performance. So the cost of signal processing and hardware will be notably increased because all of them are active elements in the transmitters and receivers. But RASs are passive elements. Using RAS in transmission also provides enhanced achievable rate while elevating the cost of physical implementation and signal processing. And here, actually, the x-axis is number of reflecting elements, y-axis is number of transmit and receive elements. We assume that 2 of them are equal to each other in that case. So if we double number of transmit and receive antennas by keeping reflecting elements constant, approximately we will obtain 2.09 bit-second hertz increase in achievable rate. So if we keep constant number of transmit and receive antennas, if we double reflecting elements, we will roughly obtain again 2.01 second hertz increase in achievable rate. So doubling, either doubling you receive antennas or reflecting elements, you will obtain good achievement, a good increase in achievable rate performance. But you don't increase the cost of signal processing when you increase number of reflecting elements. You may keep number of transmit antennas small and try to improve number of reflecting elements in the environment to achieve increase capacity or error rate performance. So let me briefly explain our coverage extension solutions for RSM powered communication systems. We have 3 different designs here. We first consider multiple array phases for both indoor and outdoors. And we also consider hybrid RSM relay assisted transmission systems. And we also consider hybrid beamforming design for RS assisted millimeter wave systems. In above 6 GHz, the signal will be more susceptible to blockage and interference, as you mentioned earlier, because collecting high energy in the receiver will be difficult due to the small antenna sizes. Therefore, the severe signal attenuation and blockage prevent millimeter waves to reach long distances. By including RAS here, you can extend that coverage for higher frequencies, as you see from that video. In order to ensure reliable wireless transmission and to alleviate these disruptive effects at high frequencies, we need to overcome the negative and uncontrollable effects of the wireless channel. The use of RAS is particularly useful when the line of sight is blocked or not strong enough, and you can provide additional transmission paths. In future wireless systems, the ubiquitous communications of many devices with various sizes are envisaged. However, it may not be reasonable to use multiple antennas or high power consuming components in those devices to enable reliable and high speed wireless transmission. You cannot improve number of antennas in the IoT devices freely. We have some limitations. So instead of improving that kind of antennas, we may improve the burden of channel medium, which is same for all devices actually, because it's in the environment and it's also all passive. So you can use multiple RASs in the environment to improve system performance. When you see that figure, we have two RASs for indoor cases, and you can activate two of them, or you can choose one of them to improve system performance, depends on your position. And in outdoor, if you want to improve and extend coverage, you can use multiple RASs. So one can be closely located to source, and another one can be closely located to the destinations, and you can use that link between the RASs, and you can adjust that phase shifts. That will increase the number of computational complexity, but you will improve the performance very well. You can also use multiple RASs, and you can make RAS selection. Depends on the channel gates. And here again, if you want to do RAS selection from that blue and orange curves, you can see that when you do RAS selection, you will improve the system performance. When you change the distance of the terminals, because dynamically you will change the active RAS elements, and you will choose the best RAS for you, and you will improve the system performance. And our another work is for collaboration with RAS and relay technologies. Most of the studies related to relaying and RASs consider one of these technologies as an alternative solutions to each other. But here we aim to find the best transmission scenarios where these two exciting technologies work in harmony with each other. Our main motivation is to design hybrid RAS and relay-aided systems with low operational complexity while keeping the advantages of RAS and relaying technologies. Two different cost-efficient schemes are proposed in this context for extending coverage by avoiding multi-hop relaying. There are that kind of system designs. You may use multi-hop relaying technologies, but you will improve the power consumption and signal processing cost. We try to find the best positioning for the RAS and the relay during that work, actually, by considering the blockage between transmitter and receiver. We propose two different designs here. In the first one, as you see from the figure 1, RAS is located to transmitter, close to transmitter. The F relay is located close to the destination. In the first time slot, we are transmitting a signal to the destination over RAS and to the F relay. And then in the second time slot, we are transmitting signal from relay to destination and from source to destination over the RAS. And this is the joint RAS and DF relay transmission design. The second one, we can integrate in these two devices. In this integrated scheme, we propose a transmission scheme where the RAS and relay are integrated in the same device and positioned in between the transmitter and receiver, as shown in that figure. In contrast to the joint design in the first figure, we assume that transmitted signal reaches the RAS relay device, which is both reflected and DF relayed to the receiver. We again assume here that the distances between transmitter and the receiver are considerably large, and that link is assumed to be blocked. For both scenarios, increasing number of elements provides a significant improvement in bit error rate over a single RAS-assisted transmission, and doubling number of reflecting elements leads to about 5 dB gain in joint design, 3 dB gain in integrated design. Okay. Let me quickly summarize also our hybrid beamforming solution. And as we know that precoding and combining is essential signal processing technique for downlink and uplink transmission. But when we consider signal stage fully digital beamforming, we will require full CSI. And we will require one power angry RF chain per each antenna, and we will obtain, we will lead to a high power consumption and hardware cost complexity in that case. So by using also analog beamformers, we can reduce that burdens, and we can reduce the number of RF chains for each antennas. And in angular-based hybrid beamforming, and we assume that we are designing the system by considering angular flow time varying channel characteristics. Channel consists of two parts, and fast time varying parameters and slow time varying parameters. Slow time varying parameters is angular information. When we use that information, we will get rid of the dependency of full CSI. And here we aim to decrease CSI overhead and number of RF chains. We use that concept, which is existing in the literature, and we collaborate with the team of Professor Lenok and Asil. You may see the details of angular beamforming from that studies. Here, in that scheme, we also include RASs. The benefits of using angular-based hybrid beamforming is reduced hardware cost complexity, reduced power consumption, reduced CSI overhead, but we will again have comparable rate performance with fully digital beamforming. Okay, RASs and massive MIMO systems can be combined here to achieve the targeted requirements for next generation communication systems. These technologies can be considered as an alternative. You may see that kind of works, but we don't want to consider like that. We may use all of the benefits of that schemes, and these schemes systems can work in harmony when you find the best operating points. In this work, we introduce an RAS-assisted angular-based hybrid beamforming system requiring low CSI overhead for millimeter wave massive MIMO systems. By considering 3D geometry-based channel model in that system, a 3-stage RAS-aided hybrid beamforming system is proposed, and we have 3 stages. First one is RF beamformers. We first design RF beamformers, then we design baseband decoder combiner, and then we need to design RAS phase shifts. This is the system model of our proposed scheme. Here we aim to design that BT, FT, FR, and BR, and then phase shift matrix of RAS. By considering this low time varying angular informations, we are designing RF stage, FT, and FR. Then, actually, at the first, we randomly determine one phase shift matrix. Then we design RF stage. Then we design baseband stage. At the end of these 2 steps, we are designing phase shift matrices again by considering particles from optimization algorithm. to obtain maximized echelon rate. We investigate the echelon rate performance in that scheme, and we consider geometry-based channel model. Here again, in the simulations, we assume that direct link is blocked. We assume 5 paths within each cluster in that cluster-based millimeter wave channel model. Here we compare the echelon rate performance for the angular-based beamforming system with or without RAS for varying transmitter RAS separation under fixed transmitter receiver positions. In this comparison, the RAS-assisted angular-based beamforming schemes with random and constant phase adjustment are also considered as a benchmark system. And it is observed that RAS significantly improves system performance when the direct link between the transmitter and receiver is nearly blocked. So here, even you use random phase adjustment, you can obtain significant improvement in echelon rate performance. But when you use PSO algorithm, you may also use different kind of algorithms, or you can do some optimization, apply some optimization methods. You will also obtain improvement in echelon rate performance. That x-axis is varying D1 distances between transmitter and RAS. The best beneficial position for RAS is not middle position. If RAS will be close to transmitter or receiver, you will obtain better performance. So these results are important in terms of also position.
May I interrupt again? What is the intuition behind this? Its operation principle is quite different from a relay. If it were a relay, on average, the best position would be the middle point. I mean, actually, it depends on the relay operation as well.
Yeah.
For an amplifier and forward relay, for example. But for a reflecting intelligent surface, you can freely say that it either needs to be close to the transmitter or the receiver. How does this happen?
Like that, because there is no any amplification in RF, but there is path loss multiplication. We have two sub-channels, transmitter RAS, receiver. Let's say we have 10-meter distances. And if you put in the middle point, if you multiply 5 by 5, you will have 25. But if you put in the 2 meters, and if you multiply 2 by 8, you will obtain 16, like that, because you don't need any, you don't have any multiplication. But in relay, if you want to amplify, you may consider to largest point, because you will lose a lot of energy and you need to regain that energy during transmission.
Thank you.
You're welcome. So let's look at our practical measurements. In that measurements, we aim to enhance the signal coverage in an indoor environment by increasing the received signal power via deployment of an RAS to the communication network. We present a demonstration of an RAS-assisted communication systems in indoor in order to enhance coverage by increasing the received signal power. And we employ an efficient algorithm, efficient codebook algorithm for RAS configurations to reduce the requirements of the feedback. When you check that video, you may have a base station on top of the building, and you may have that kind of RAS in the next building. So there is no direct link between transmitter and receiver, but there are, continuous zones for receiver. You may reflect signal for each point for RAS, but you need you will have high complexity when you calculate the best phase adjustment. Instead of this, you can slice environment, and you can just determine a limited discrete number of reflection scenarios. So I mean that, for example, you may slice that environment by 2. And in that case, you will have in transmitter, you have fixed position. In RAS, you have fixed position. If you have two saved code words, for first one, you can radiate signal to first one. The second one, you can roughly direct signal to the second zone. So if receiver in the second zone, you can improve the system performance. This is not the best case, but you may reduce the computational complexity during the transmission. And you may just save 2 code books, but 2 is not enough. You may divide environment by 4, 8, like that, and you may save just limited number of code books for RAS. And you just need location information and receiver. This is our target during our measurements. Here we use RAS prototype developed by Greener Wave company at 5 GHz. We have 76 reflecting elements whose reflection coefficient can be adjusted with PIN diodes. And we have, if we have 76 elements, we have total 2 to the 76 combinations and possible configurations for RAS. We have 2 states for each element, on-off states for PIN diodes, and we can configure phase shifts by changing that on-off state 0 or 118 degree. On state means off state means 0 degree phase shifts. On state means 180 degree phase shifts. We use horn antennas in the transmitter and the receiver, and we use iterative method attempts to find the RAS configuration which allow incoming signals to be reflected at the desired angle. In that iterative method, initially all elements are set to off, indicating that RAS is no phase shift mode. You can just think that a metal plate, if all elements are in the off case. Then you are starting from the first element. You are changing off to on. If receive signal will be improved, you will keep on. Then go to the second one. If on case will improve, keep on, or off case is better, keep off, and then you will have 76 steps in phase adjustment instead of 2 to the 76 possible configurations. But normally in each receiver positioning, you need to obtain that phase adjustment. But again, you can see that our indoor setup, we have transmitter, receiver, and RAS here. And we don't have direct link between transmitter and receiver. The whole view of our transmission setup is L-shaped corridor, like that. And this is the top view of our simulation setup. That blue one is RAS. The green one is transmitter. These are in the fixed positions. And we are slicing that environment in 7 areas. We have 7 different areas. It's equally departed. And we have, circle points for test points. We have 1, 2, 3, 4, 5, 6 test points for that lines. For example, for first point, that point, we are measuring the received signal and finding the best RAS configurations. Then we take that code words for RAS or that line. For second, we are also calculating the best phase adjustment, and we are keeping that. And for these other points, we are keeping the maximized RAS configurations. But we have just 6 measurements to calculate that best configurations. And then these square points is the user. If user in the location one, we are checking that which line is closer to that point. If the first line is closed, we are using the code words which is saved for that point. So, or if location this users goes from location 1 to location 2, we are again calculating the location and say that this is closer to the second line. So we are using that configurations. And here is the solution. Here, received signal powers are measured and compared for the 3 cases where first, RAS is no phase shift mode. This is the yellow line. Second, the offline code verse of the stored codebook of the closest point is applied to the RAS. This is the iterative algorithm that I mentioned, the blue one. And third, the configuration of the online iterative methods. This means for location 1, you are considering all possible configurations, 76 configurations to find best configurations. For location 1, again, for each point, you should do online training for all points. This is the ideal case for iterative methods. But here, we reduce the number of calculation steps to obtain, reasonable performance. And here, it can be observed from that figure. The RAS configured with the code verse tends to keep, as you see, received signal powers above 30 dB, even when the RX moves further distances. You don't have ideal online training, but even we will have very reasonable performances. It's very close to online case. The performance of the codebook for locations where this angle are close to the angles of the saved code verse is achieved very close to the results of online iterative configurations. So we can reduce that complexity, but again, we can go one step beyond. Normally in iterative algorithm, we have 76 steps, but we can make subgrouping. It means you can make iterative algorithm for each element, or you can go for 2 by 2. You can think that two together. On, off, off. It depends on the adjacent cell when you compare. Or you can make subgrouping for 4 by 4 or 8 by 8. Here you will obtain 19 steps, and here you will obtain just 9 steps for iterative decoding. Here the performance of that steps, the red is group of 1 by 1, blue is group of 2 by 2, red is group of 4 by 4, and the black one is group of 8 by 8. The 1 by 1 is best solution in terms of accelerate performance, but again in this x-axis is the total number of iterations. We are reducing the total number of iterations, but we again obtain very good error performance, very good accelerate performance. So you can reduce significantly total computational complexity because we are depending end-to-end channel. By considering end-to-end channel, we are calculating receive signal. We are also calculating, we may also calculate different parameters to maximize the performance here. So employing the grouping approach will reduce the time and effort required to optimize the RAS configurations. We have some practical measurements for outdoor environments, but it's still in progress. You may also check the details from that our ICC paper. We are also working different kind of practical measurements nowadays. I am also working on terrace applications of RAS, hybrid beamformings, or the practical RAS by considering zero CSI. If we don't have CSI, how can we improve system performance? Actually, I am now working on that kind of problems, that kind of topics, to make RAS implementation efficient, to reduce cost of the RAS implementation. We are thinking in that way. We start from the channel modeling because we want to understand the efficiency of RAS in the environment. Then we started to design systems by considering that spatial, features of arrays. These are the publications that I mentioned during the presentation. And if you have any additional questions, we can also discuss by considering that.
Thank you very much for this nice presentation.